Before sleep begins, the universe opens on a darkness so large that even light cannot return. TON 618 is often called one of the largest black holes ever found, with a mass that may reach tens of billions of suns. Around it, gas burns brighter than entire galaxies, while the center remains completely hidden. This is the story of its size, its mass, and the mystery still waiting beyond the edge of light. If this quiet journey's welcome, please like the video and subscribe to the channel. Far beyond the visible patterns of nearby stars, far outside the familiar structure of the Milky Way, there exists a region of space where distances stretch into scales that resist ordinary description. In this distant setting, the quasar known as TON 618 resides, appearing not as a distinct shape but as a concentrated point of intense brightness embedded within the deep darkness of the universe. The light that marks its presence does not belong to a nearby era. It begins its journey billions of years in the past, at a time when galaxies are younger, less settled, and more active than those in the present epoch. In this outermost region of consideration, the environment is defined not by solid surfaces or defined boundaries, but by the vast, diffuse fabric of space itself. The background is filled with faint radiation, the residual glow from the early universe, along with scattered galaxies whose light is softened by distance. Between these galaxies lies an immense expanse where matter is thinly distributed, composed mostly of hydrogen and helium gas, along with invisible dark matter that shapes large-scale structure through gravity. The density of this region is extremely low, yet it plays a crucial role in guiding the paths of light and matter over immense distances. TON 618 stands out within this quiet expanse because of its extraordinary brightness. Despite its immense distance, it shines with a power that surpasses entire galaxies. This brightness is not constant in appearance when observed over long periods. Careful measurements show subtle variations, indicating that the source of light is compact and energetic. Observations indicate that such variability is a key property of quasars, suggesting that the energy originates from a relatively small region compared to the vast scales of galaxies. The surrounding cosmic field is structured by the slow expansion of the universe. Over time, the space between distant objects increases, stretching the wavelength of light that travels through it. As a result, the light from TON 618 arrives at observers in a shifted form, appearing redder than when it was first emitted. This effect, known as redshift, provides a measure of how far the light has travelled and how much the universe has expanded during that journey for TON 618. The redshift is significant, indicating that its light began travelling when the universe is much younger than it is now. In this outer region, the influence of gravity is subtle yet pervasive. Large clusters of galaxies exert a collective pull that bends the paths of light, a process known as gravitational lensing. While TON 618 is not strongly distorted by such effects in most observations, the possibility remains that unseen structures along the line of sight may slightly alter the brightness or position of its image. Observations indicate that such influences are generally small in this case, but they form part of the broader environment through which the light passes. The cosmic background against which TON 618 is seen is not entirely empty. It contains a faint distribution of intergalactic gas, which can absorb certain wavelengths of light. As the light from the quasar travels inward through this medium, it encounters clouds of hydrogen that leave characteristic absorption features in the observed spectrum. These features provide indirect information about the structure and composition of the space between galaxies. They reveal that even in the most diffuse regions, matter is present and interacts with passing radiation. The outer setting is also shaped by the history of cosmic structure formation. In the early universe, small fluctuations in density grow over time under the influence of gravity, forming the first stars and galaxies. TON 618 exists within this evolving framework, positioned in a region that has accumulated enough matter to form a massive galaxy and its central engine. Observations indicate that quasars like TO and 618 are more common in earlier cosmic times, suggesting that the processes that power them are linked to phases of rapid growth and change. At this scale, the concept of direction becomes less meaningful. There is no central point or preferred orientation in the universe as a whole. Instead, this setting is defined by relative distances and the paths that light follows between objects. TON 618 is identified not by its location in a fixed coordinate system, but by its measurable properties, including its brightness, spectrum, and redshift. These properties allow astronomers to place it within the broader map of the universe. Even though it lies far beyond any region that can be directly explored, the light from TON 618 is not continuous across all wavelengths. It spans a wide range, from radio waves to visible light, and into higher energy regions of the spectrum. However, as it travels across the outer cosmic environment, different wavelengths are affected in different ways. Some are absorbed by intervening material, while others pass through relatively unimpeded. Observations across multiple wavelengths provide a more complete picture of the quasar and its surroundings, revealing both the properties of the source and the characteristics of the space it inhabits. In this distant setting, time itself takes on a layered quality. The light observed today represents a moment from the past, preserved across billions of years of travel. The quasar as it appears now may have changed significantly since that light was emitted. It remains uncertain whether TON 618 still shines with the same intensity, or whether its central activity has diminished. Observations indicate only the state captured in the arriving light, leaving the present condition unknown. The outer region is therefore defined by distance, by the expansion of space, and by the long journey of light. It is a quiet domain, where processes occur on timescales far beyond human experience. Within this domain, TON 618 is a distant beacon, its brightness marking the presence of an extreme object hidden deeper within. The surrounding environment does not reveal its structure directly, but it provides the stage upon which its light travels, carrying information inward toward observation. As attention remains fixed on this outermost region, the focus stays on the broad context rather than the details of the source itself. The vastness of space, the faint distribution of matter, and the slow expansion of the universe define the conditions under which the quasar is observed. Only by considering this setting can the inward path toward the object begin, guided by the light that crosses these immense distances. The light from TON 618 begins its long passage through space in an earlier age of the universe. It leaves a region of strong brightness and enters the wider darkness, carrying with it the imprint of the conditions around its source. Once it is released, it travels outward in every direction, moving through a universe that is not fixed in size. The space through which it moves continues to expand during the journey, and this expansion slowly changes the light itself. In ordinary experience, light may seem immediate, but across cosmic distances it becomes a messenger from the past. The light from TON 618 crosses billions of light-years before reaching telescopes near Earth. A light-year is the distance light travels in 1 year through empty space. Because the universe expands while the light is in motion, the travel distance and the present separation are not the same simple measure. Astronomers describe these distances carefully, using redshift and cosmological models to understand how far away the source is and how long the light has been travelling. As the light moves through expanding space, its wavelengths stretch. A wavelength is the distance from one crest of a light wave to the next. When that distance becomes longer, the light shifts toward the red part of the spectrum, and then beyond visible red into infrared wavelengths. This stretching is not caused by the light slowing down. In empty space, light continues to move at the same fundamental speed. The change happens because the fabric of space itself grows during the journey, carrying the light along a path that lengthens with time. This redshift is one of the main ways TON 618 is placed in the history of the universe. Its measured redshift shows that the light was emitted when the cosmos is much younger than it is in the present day. The object is not merely far away in space, it is also far away in time. Observations of its light therefore reveal conditions from an earlier cosmic era, when large galaxies and their central black holes are still undergoing major growth. The arriving light is a record of that era, preserved by its journey across the expanding universe. Along the path, the light passes through regions that are almost empty, but not perfectly empty. Thin gas lies between galaxies. This gas is mostly hydrogen, the simplest and most abundant element. When the quasar's light crosses clouds of hydrogen, certain wavelengths are absorbed. These missing wavelengths appear as dark features in the spectrum, which is the spread of light arranged by wavelength. The pattern of these absorption features allows astronomers to study material that's otherwise too faint to see directly. The most common of these features is connected with hydrogen absorbing ultraviolet light. As the universe expands, light absorbed by different clouds appears shifted by different amounts, depending on the distance of each cloud. The result is a layered pattern along the line of sight. This pattern does not describe the black hole directly. It describes the space between the quasar and Earth. It shows that the path is filled with traces of matter, arranged in clouds, filaments, and diffuse regions shaped by gravity over cosmic time. Some parts of the light are weakened by dust. Cosmic dust consists of tiny solid grains made from heavier elements formed in stars and spread by stellar winds and supernova explosions. Dust can absorb and scatter shorter wavelengths more effectively than longer ones, making distant light appear dimmer or redder. Along the path from TON 618, the effect of dust must be considered when measuring the object's true brightness. Observations use models and comparisons across wavelengths to separate the changes caused by distance, expansion, gas, and dust. The light also crosses the gravitational fields of galaxies and dark matter structures. Gravity can bend the path of light, even when the light does not pass through visible matter. This bending is predicted by general relativity, the theory in which gravity is understood as the curvature of space and time. In many distant observations, gravitational bending may slightly magnify or distort background sources. For TON 618, the main observed brightness is understood as intrinsic to the quasar rather than the result of strong lensing, though small effects from intervening structures remain part of the observational environment. During the journey, the light does not carry a simple image like a nearby photograph. It carries a spectrum, a brightness pattern, and changes over time. These features are collected by telescopes and instruments, then compared with physical models. The spectrum contains broad and narrow features produced by gas moving at different speeds near the source, as well as absorption features from matter along the path. At this stage of the inward exploration, the important fact is that the ancient light carries both local information from its origin and added marks from its travel. The journey also shows why direct observation of such an object depends on patience and inference. No telescope sees TON 618 as a resolved central structure in the way it might see a nearby planet or nebula. The angular size is too small, and the distance is too great. Instead, its nature is understood from the behavior of light. Brightness, color, variability, and spectral features become the tools that replace direct closeness. Each measured property is affected by the long path across the universe and must be interpreted with care. As the light nears the region of the Milky Way, it enters a different foreground environment. It passes through gas and dust belonging to the galaxy that contains the solar system. This material can add further absorption and reddening, though it is far closer than the distant intergalactic clouds. Astronomers account for this foreground effect when estimating the true properties of TON 618. The measurement is therefore not a single act of seeing, but a process of removing known influences and preserving the signal that began far away. The ancient light path is a bridge between the remote quasar and present observation. It does not reveal everything at once. It carries information altered by expansion, marked by gas, softened by dust, and guided by gravity. These changes do not erase the signal. They make it richer, because they show both the distant source and the universe between. In this region of the exploration, the light remains the subject, moving across cosmic distance as a quiet record of an earlier time, before it is gathered and read by instruments near Earth. Around TON 618, the visible identity of the system is dominated by the quasar environment. A quasar is the bright active center of a distant galaxy, powered by material falling toward a central black hole. From the outside, this environment does not appear as a calm galaxy with a clear spiral shape or a soft oval glow. It appears instead as an intense source of radiation, so bright that the surrounding galaxy becomes difficult to separate from the central light. The quasar is the outer visible sign of a much deeper gravitational engine. In this region, the light is not produced by the black hole itself. A black hole gives off no light from inside its boundary. The brightness comes from matter outside that boundary, especially gas that is heated as it moves through the central region. This distinction is important. TON 618 is known through its quasar light, and the black hole is inferred from the energy, motion, and scale of the material producing that light. The quasar environment is therefore both a veil and a clue. It hides the central object in glare, while also revealing its presence through the power of that glare. The quasar's radiation covers a wide range of wavelengths. Some of it is visible light, some is ultraviolet light, and some appears at longer and shorter wavelengths that instruments can measure. The wide spread of energy suggests several physical regions working together. Hot gas produces strong ultraviolet and visible emission. Cooler dust farther out absorbs part of the radiation and releases it again as infrared light. Fast-moving charged particles may add radiation at radio wavelengths in some quasars, depending on the structure of their outflows and jets. TON 618 is studied through this mixture of signals, each one carrying a different part of the environment's story. The surrounding gas is shaped by radiation pressure, gravity, and motion. Radiation pressure is the push that light can exert on matter. Near a quasar, this push can be strong enough to affect gas clouds, lifting or driving some material outward, even as other material continues inward. Gravity pulls matter toward the center, while heat and radiation can resist that inward motion. The result is not a simple fall, but a complex region of moving gas, glowing clouds, and changing brightness. The quasar environment is also marked by ionization. Ionization occurs when atoms lose electrons after absorbing enough energy. The intense radiation from TON 618 removes electrons from hydrogen, helium, and heavier elements in nearby gas. When electrons later recombine with atoms or shift between energy states, the gas emits light at specific wavelengths. These emissions create lines in the spectrum. They're not drawn lines in space, but measured features in the spread of light. Their strength and width help astronomers understand the conditions around the quasar. In the outer quasar environment, some gas is relatively extended and less dense. It may form a narrow line region, where gas moves more slowly compared with material closer in. The term narrow line region refers to gas whose emission features appear relatively narrow in the spectrum because the gas has lower speeds along the line of sight. This region may stretch across large parts of the galactic center. It is illuminated by the quasar's radiation and responds by glowing in selected wavelengths. Its presence shows that the central source affects material beyond the smallest inner zones. The quasar light can overpower the host galaxy because the energy release is extraordinarily efficient. When gas falls into a deep gravitational field, a portion of its mass energy is converted into radiation before the gas crosses the black hole boundary. This process can release more energy per unit of mass than ordinary nuclear fusion in stars. The visible result is a central region able to shine more brightly than hundreds of billions of stars. For TON 618, the observed brightness is one of the reasons its central black hole is understood to be exceptionally massive. The environment is not perfectly steady. Quasars can vary because the flow of matter is uneven. Gas may arrive in clumps, turbulence may change the heating of the disk, and magnetic fields may shift the way energy moves through the region. Observations of variability provide evidence that the source of much of the light is compact. A very large object cannot change its whole brightness quickly, because light needs time to cross it. When a quasar changes over measured intervals, those changes help constrain the size of the emitting region. Dust also forms part of the quasar environment, though it cannot survive everywhere. Too close to the central brightness, dust grains are heated until they break apart or evaporate. Farther out, dust can remain intact, arranged in clouds or a thicker obscuring structure. This dusty material absorbs high-energy radiation and releases softer infrared light. Depending on viewing angle, dust can partly hide the central regions of some active galaxies. TON 618 is seen as a bright quasar, meaning that the line of sight allows powerful central light to reach observers. The quasar environment may also include outflowing gas. Outflows are streams of material pushed away from the center by radiation, winds, or magnetic forces. In spectra, such outflows can appear as absorption features shifted toward shorter wavelengths, showing gas moving toward the observer relative to the quasar. These winds matter because they can carry energy and material into the surrounding galaxy. They may heat gas, slow star formation, or change the supply of matter available near the center. Observations of quasars show that such feedback can be important, though the precise details vary from object to object. In TON 618, the extreme brightness indicates that the central engine is not quiet. It is in an active phase, with matter available near the black hole and enough energy released to illuminate a vast region. The quasar environment is therefore a sign of growth or recent feeding. It does not show the entire history of the black hole, but it captures one luminous stage. The central mass may have grown over long periods through gas accretion and mergers. Yet the quasar phase is the visible moment when that growth becomes radiant. The outer quasar environment remains a region of interpretation rather than direct close viewing. Its structures are too small and too distant to be mapped like nearby clouds in the Milky Way. Astronomers instead read the spectrum, compare brightness across wavelengths, and use physical models of heated gas, dust, and radiation. The picture that emerges is consistent with an active galactic nucleus of extraordinary power. The quasar light fills the observational field, while the hidden mass at the center shapes the motions and energy that make the system visible across the universe. Around the bright quasar system lies a wider region of gas that is much larger and more diffuse than the compact central glow. This region is often discussed through the presence of a Lyman alpha nebula, a vast cloud whose light is linked to hydrogen. Lyman alpha radiation is ultraviolet light emitted when an electron in a hydrogen atom moves from a higher energy state to a lower one. In distant objects, this ultraviolet light is stretched by the expansion of the universe, so instruments may detect it at longer wavelengths than when it first leaves the gas. The nebula associated with TON 618 is not a solid shell or a sharply bounded object. It is a broad, luminous structure made of thin gas spread across an immense region around the quasar. Its brightness is faint compared with the central quasar, but its scale is large. Observations indicate that such nebulae can extend far beyond the immediate galaxy, reaching into the surrounding circumgalactic region. The circumgalactic region is the zone of gas around a galaxy, outside the main body of stars but still influenced by the galaxy's gravity and activity. In this outer gas, hydrogen is the main actor. The quasar's intense radiation pours outward and strikes atoms in the surrounding material. Some hydrogen atoms absorb high-energy photons and lose their electrons. Later, as electrons return and settle into lower energy states, they release light at characteristic wavelengths. The Lyman alpha line is one of the strongest of these features. It becomes a way to trace gas that would otherwise be nearly invisible, because the gas is too thin and too spread out to shine brightly on its own. The shape of a Lyman alpha nebula is not always simple. It may be uneven, stretched, or clumpy, depending on the distribution of gas, the direction of radiation, and the motion of material in the surrounding environment. Some parts may glow more strongly because they are denser or receive more direct illumination from the quasar. Other parts may appear dimmer because the gas is thinner, more shielded, or moving in ways that shift the emitted light. The observed structure is therefore a map of both matter and radiation. This gas is part of the larger environment in which massive galaxies grow. In the early universe, galaxies draw material from surrounding filaments of gas and dark matter. Filaments are long, thread-like structures in the cosmic web, the large-scale pattern formed by gravity. Gas can move along these structures toward galaxies, while energetic activity from the center can also drive gas outward. The nebula around a quasar may contain material involved in this exchange. It may include gas falling inward, gas being pushed outward, or gas stirred by interactions with nearby structures. Observations can show motion through shifted spectral lines, but the full three-dimensional flow remains difficult to reconstruct. The light from the nebula is also affected by scattering. Lyman alpha photons do not always travel directly out of the gas after they are produced. Hydrogen atoms can absorb and re-emit them many times, changing their direction before they escape. This process makes Lyman alpha light especially complex to interpret. A bright patch may not mark the exact place where the light was first produced. It may show where photons finally emerge after many interactions. For this reason, the nebula is both a physical cloud and a radiative pattern shaped by repeated scattering. Dust can reduce the escaping Lyman alpha light. Even a small amount of dust mixed with gas can absorb photons during their repeated path through the nebula. Because Lyman alpha photons may scatter many times, their total travel distance inside the gas can be much longer than a straight line. This increases the chance of absorption by dust grains. The amount of observed light therefore depends not only on how much hydrogen is present, but also on the dust content, gas motion, and geometry of the region. The quasar's energy reaches far into this outer gas. Its radiation can ionize material across large distances, creating an extended glow. This shows that the central engine has enough power to influence regions well beyond the compact nucleus. The nebula acts like a quiet record of that influence. It does not reveal the black hole directly, but it shows the reach of the radiation generated by matter near the black hole. In this sense, the outer gas becomes a visible boundary of the quasar's impact on its surroundings. The nebula region also connects to the question of how such a massive system has enough fuel. A black hole of extreme mass cannot grow without a long supply of material. The surrounding galaxy and its gas reservoir must provide matter over cosmic time. The extended gas traced by Lyman alpha emission may represent part of the wider supply network around the galaxy, though it does not prove a direct path into the black hole. It shows that the environment contains large amounts of gas, but the detailed movement of that gas toward the central regions remains uncertain. The glow of the nebula is faint and difficult to measure because it surrounds a much brighter quasar. Instruments must separate the intense point-like central emission from the extended light around it. This requires careful observation and processing. The central quasar can scatter in the telescope optics and mask weaker structures nearby. When the extended emission is detected, it provides valuable evidence about gas on scales that are otherwise hidden by distance and glare. In this region, the focus remains outside the main stellar body of the host galaxy and outside the compact active center. The nebula belongs to the broader gaseous atmosphere of the system. It is thin, extended, and illuminated from within by an energy source far more concentrated than the cloud itself. Its presence shows that TON 618 is not only a bright point in the distant universe, it is surrounded by material that responds to its radiation across a large volume of space. The Lyman alpha nebula therefore forms a soft outer layer in the inward path. It is a region where hydrogen gas, radiation, dust, and motion interact across great distances. The science of this region depends on faint light and careful interpretation. Observations indicate an extended gaseous environment around the quasar, while the exact distribution and motion of all the gas remain uncertain. The nebula is not the black hole and not the core. It is the wide, illuminated field around the system, marking the reach of central power through the quiet language of hydrogen light. Within the wider gas surrounding TON 618 lies the region of the host galaxy, the great stellar system that contains the quasar at its center. At such a distance, the host galaxy is difficult to separate from the glare of the active nucleus. The quasar light dominates the view, washing over the softer and more extended glow of stars. Even so, the host galaxy remains essential. It is the gravitational home of the central black hole, the larger structure that gathers stars, gas, dust, and dark matter into one bound system. The host galaxy is not observed in the same clear way as a nearby galaxy with visible arms, dust lanes, or a bright central bulge. Its details are hidden by distance and by the brilliance of the quasar. Astronomers infer many of its properties from the behavior of the central source, from the surrounding gas, and from comparisons with other quasar-host galaxies. Observations indicate that extremely luminous quasars usually live in massive galaxies, often in systems with large supplies of gas. For TON 618, the scale of the central black hole suggests a host of great mass, though the exact stellar structure remains difficult to measure. A galaxy is a system held together by gravity, containing stars, gas, dust, stellar remnants, and dark matter. The visible stars may form a disk, an oval body, or a disturbed shape depending on the galaxy's history. In the early universe, when the light from TON 618 begins its journey, many massive galaxies are still growing actively. Some are forming stars at high rates, some are merging with other galaxies, some are feeding their central black holes through flows of gas driven inward by gravitational disturbances. The host of TON 618 belongs to this broader era of energetic growth. The stars in the host galaxy provide a quieter form of light than the quasar. Stellar light comes from nuclear fusion in the cores of stars, where hydrogen and other elements release energy over long timescales. This light is steady compared with the changing brightness of an active nucleus. Yet in TON 618, the central quasar is so luminous that the ordinary starlight becomes hard to isolate. The host galaxy may contain hundreds of billions of stars, but their combined glow can still be overwhelmed by the compact central engine. Gas within the host galaxy plays a major role in shaping both star formation and black hole activity. Cold gas can collapse into dense clouds where stars form. Warmer gas can fill the spaces between stars. Hot gas may be produced by stellar explosions, winds, and energetic activity from the center. In a quasar host, some gas may move inward and feed the active nucleus, while some may be heated or pushed outward by radiation and winds. The galaxy is therefore not a still container. It is a moving system where material changes phase, direction, and density over time. Dust is also present in the host galaxy. It gathers in clouds, absorbs shorter wavelength light, and re-radiates energy at longer wavelengths. Dust marks regions where heavier elements exist, because dust grains are built from elements forged in earlier generations of stars. In distant quasar hosts, dust can hide star-forming regions and complicate estimates of the galaxy's true brightness. Infrared observations help reveal dust-warmed emission, offering another way to study the host when visible light is dominated by the quasar. The dark matter halo around the host galaxy forms an invisible outer framework. Dark matter does not emit or absorb light in ordinary ways, but its gravity affects the motion of gas and stars. Massive galaxies are thought to sit within large dark matter halos, which help gather ordinary matter from the surrounding cosmic web. The host of an extremely luminous quasar likely occupies a dense region where enough matter has collected to support both galaxy growth and black hole growth. The exact mass of the halo is uncertain, but its presence is part of the standard understanding of galaxy formation. The relationship between the host galaxy and the central black hole is one of the central themes in modern astrophysics. In nearby galaxies, black hole mass often correlates with properties of the central stellar bulge, such as the motion of stars and the total stellar mass. These correlations suggest that galaxies and their central black holes influence one another over long timescales. For an extreme object like TON 618, the central black hole appears extraordinarily massive, and it remains uncertain how closely its host follows the same relationship seen in nearby, quieter galaxies. The host galaxy may have experienced mergers. A merger occurs when two galaxies pass close enough that gravity draws them together into one system. Such events can disturb gas and drive some of it toward the center. They can also build larger stellar bodies and alter the shape of the galaxy. In the early universe, mergers are more common than in the present day because galaxies are closer together on average, and many systems are still assembling. Observations of quasar hosts often show signs of disturbed structures, though for TON 618 the glare and distance make detailed confirmation difficult. Star formation in the host galaxy may occur alongside quasar activity. The same gas-rich conditions that feed a central black hole can also support the birth of new stars. Yet the quasar can also affect this process. Energy from the active center can heat gas or push it outward, reducing the amount available for star formation. In other cases, pressure from outflows may compress gas and encourage local collapse. The balance depends on the structure and motion of the gas. For TON 618, the broader principle is clear. While the exact state of star formation remains uncertain, the host galaxy region is therefore a place of hidden complexity. It is larger and slower than the active center, but it supplies the material and gravitational setting that make the quasar possible. Its stars carry the history of earlier growth. Its gas and dust reveal ongoing change. Its dark matter halo anchors the system within the larger cosmic web. The central brightness makes the galaxy hard to see, but not unimportant. Behind the quasar's glare, the host remains the body within which the extreme black hole has formed, grown, and become visible through the activity at its core. Closer to the center of the host galaxy, the broad stellar system gives way to a denser galactic core. This region is still much larger than the black hole itself, yet it is shaped more strongly by the gravity of the central mass and by the gathering of stars, gas, and dust into a compact inner volume. The glow here is not spread as gently as it is in the outer parts of a galaxy. It is more concentrated, more crowded, and more affected by motion around the center. In the galactic core, stars move along paths controlled by the combined gravity of the galaxy and the central black hole. These paths are not simple circles. They may be stretched, tilted, or disturbed by the pull of nearby stars, gas clouds, and the central mass. In a distant quasar host like TON 618, individual stars cannot be separated, but the general principle remains clear. A massive central object increases the speed of nearby material, and the closer matter lies to the center. The more strongly gravity shapes its motion. The density of stars in a galactic core can be high compared with the quieter outer galaxy. Many stars occupy a smaller volume, and their collective light forms a bright central concentration. Some may be old stars that formed during earlier phases of the galaxy's history. Others may be younger stars born from dense gas that collected near the center. The exact mixture in TON 618 is difficult to observe directly because the quasar outshines the host. But massive active galaxies commonly contain compact central stellar regions built over long periods of growth. Gas in the galactic core behaves differently from stars because gas can collide, cool, heat, and lose energy. Stars mostly pass near one another without direct contact, but gas clouds interact. When gas clouds collide or compress, they can radiate energy away and settle into new structures. This ability allows gas to move inward more effectively than stars. In the core of an active galaxy, the motion of gas becomes especially important because it may provide the material that eventually powers the quasar. The inward movement of gas is not automatic. Gas usually carries angular momentum, which is the tendency of rotating material to keep circling rather than falling straight inward. To move closer to the center, gas must lose some of this angular momentum. Disturbances in the galaxy can help. A bar-shaped stellar structure, a merger, gravitational tides, or turbulence can shift gas from wider orbits into smaller ones in the dense core. These processes may guide material toward the central active region, though the exact route is complex and often uneven. Dust follows much of the gas, collecting in thicker clouds and lanes where material is cooler and denser. In the galactic core, dust can obscure parts of the central environment. It absorbs ultraviolet and visible light, then releases energy at infrared wavelengths. This dust does not simply hide the region. It also helps trace where gas is concentrated and where energy from the quasar is being absorbed. in a system as bright as TON 618. Dust near the center must exist at distances where it can survive the intense radiation without being destroyed. The galactic core is also a place where feedback from the quasar begins to affect the host more directly. Feedback means the influence of energy released near the black hole on the surrounding galaxy. Radiation, winds, and possibly jets can heat gas, stir it, or drive it outward. This can change the amount of fuel available for both star formation and continued black hole growth. The core becomes a meeting region, where material may be pulled inward by gravity, while other material is pushed outward by energy from the active center. The balance between inflow and outflow is not fixed. At some times, gas may collect and move inward, increasing the brightness of the quasar. At other times, radiation and winds may clear or heat the inner gas, reducing the supply. Observations of active galaxies show that these processes can occur together. Some gas moves toward the center while other gas escapes or circulates. For TON 618, the extreme luminosity indicates that a powerful central engine is active, but the detailed pattern of gas flow in the core remains uncertain. The gravitational field in the core is not produced only by the black hole. Stars, gas, and dark matter also contribute. Farther from the center, the mass of the galaxy can dominate the motion. Closer in, the black hole's gravity becomes more important. The region where the black hole's influence is stronger than the random motion of surrounding stars is called its sphere of influence. For an ultra-massive black hole, this region can be unusually large compared with that of smaller black holes. Although at the distance of TON 618, it cannot be directly resolved with ordinary imaging. Within the core, the radiation from the active nucleus changes the state of nearby gas. Atoms can be ionized, molecules can be broken apart, and dust grains can be heated. Some gas becomes too hot to collapse into stars, some may cool in shielded regions. The core is therefore not uniform. It contains layers and pockets of material at different temperatures and densities, all affected by distance from the central light source and by the shielding provided by dust and gas. This region also stores clues about the history of growth. A black hole as massive as the one inferred in TON 618 likely forms through long periods of accretion, merges with other black holes, or both. The galactic core would record some of that history through its stellar density, gas distribution, and possible disturbances. Direct evidence is limited by distance and glare, so the interpretation relies on comparisons with other massive galaxies and active galactic nuclei. Observations indicate that such extreme systems require efficient early growth, while the exact sequence of events remains uncertain. The galactic core approach is a transition from the large host galaxy to the compact active center. It is still a region of stars and interstellar matter, but the motions grow faster and the radiation field grows stronger. Gravity gathers material inward, while light and winds push against it. The result is a dense, changing environment where the host galaxy's broader structure begins to give way to the central engine. The black hole itself remains hidden deeper inside, but its influence is already present in the crowded motions and altered gas of the core. At the compact center of the host galaxy lies the active galactic nucleus, the small and powerful region that gives TON 618 its quasar identity. An active galactic nucleus is the bright central zone of a galaxy, where matter near a supermassive black hole releases immense energy. It is not the full galaxy, and it is not the black hole alone. It is the working environment around the hidden mass, where gas, dust, radiation, and gravity meet in a confined space and produce a brightness visible across billions of light years. In this region, the scale narrows greatly. The host galaxy may contain hundreds of billions of stars across many thousands of light years, but the active nucleus occupies a much smaller central volume. Its light can still exceed the light of the whole surrounding galaxy because the process powering it is highly efficient. Gas falling into a deep gravitational field loses energy as it moves inward. That energy becomes heat and radiation before the gas reaches the event horizon. The event horizon is the boundary beyond which no light can escape. At this stage of the inward path, the boundary itself remains hidden deeper inside, while the active nucleus shines outside it. The active nucleus of TON 618 is observed as exceptionally luminous. This luminosity means that the central region releases energy at a rate far beyond ordinary stellar systems. Stars produce light through nuclear fusion, a process that unfolds steadily in their cores. The active nucleus produces light through gravitational energy, as matter is drawn into an extreme central field. The gas does not fall quietly. It moves in orbit, collides with other gas, compresses, heats, and radiates. The result is a compact source of light that appears almost point-like to distant telescopes. The nucleus contains several linked zones, though they cannot be directly separated in a simple image. There is hot gas producing continuous radiation, clouds moving at high speeds, dust located far enough away to survive, and perhaps outflowing winds shaped by radiation and magnetic fields. Each part contributes to the observed spectrum. Some light comes as a smooth continuum, spread over many wavelengths. Some appears as emission lines from atoms in moving gas. Some is absorbed and re-emitted by dust. Together, these features reveal the inner activity even when the structure itself is unresolved. The energy in the active nucleus affects the state of matter nearby. Gas becomes ionized by intense ultraviolet and X-ray radiation. Ionized gas has lost electrons and responds strongly to electric and magnetic forces. This makes the region dynamic, because charged particles can be guided, heated, and accelerated by magnetic fields. Magnetic fields may also help move angular momentum through the gas, allowing some material to drift inward while other material carries motion outward. This process helps explain how gas can continue moving toward the center instead of remaining in stable orbit. The active nucleus is not a solid object with a surface. It is a layered physical process. At larger distances within the nucleus, dust and cooler gas can exist. Closer in, dust grains cannot survive the radiation and heat, leaving mostly atomic and ionized gas. The closer material orbits, the faster it moves. These speeds are not measured by watching clouds cross the sky because the system is too far away. They are measured through the broadening of spectral lines, where light from gas moving at many velocities spreads across a wider range of wavelengths. The brightness of the active nucleus must remain within limits set by gravity and radiation. When radiation pushes outward on gas and gravity pulls inward, a balance can be described by the Eddington limit. This limit is not a hard wall for every detailed situation, but it provides a useful scale for how brightly matter can shine while still being held by gravity. A more massive black hole can support a higher luminosity before radiation pressure becomes dominant. The extreme brightness of TON 618 is therefore consistent with an exceptionally massive central black hole. Variability gives another clue to the compact nature of the active nucleus. When brightness changes, the timing of those changes places limits on the size of the emitting region. A region cannot vary as one unit faster than light can cross it. Observed changes in quasars show that much of their light comes from relatively compact zones compared with the size of the host galaxy. In TON 618, The central brightness is steady enough to be identified across surveys. Yet like other quasars, it belongs to a class of objects where change over time is part of the evidence for compact activity. The active nucleus also shapes the nearby surroundings through outflows. Radiation from the center can push on gas, especially when the gas contains ions that absorb specific wavelengths. Winds may rise from the disk or from regions above it, carrying material away from the central engine. These winds can leave marks in the spectrum, such as shifted absorption features. They show that the nucleus does not only draw matter inward, it can also return energy and material outward into the galactic core. The structure of the active nucleus depends partly on viewing angle. In some active galaxies, dust blocks the direct view of the hottest central regions, making the nucleus appear dimmer at visible and ultraviolet wavelengths. In others, the line of sight is more open, allowing the bright inner source to be seen directly. TON 618 is observed as a powerful quasar, which means that its central radiation reaches observers without being fully hidden by surrounding dust. This does not mean dust is absent. It means that the path of light from the brightest regions remains largely accessible. At this depth, the science becomes increasingly indirect. No instrument forms a detailed picture of the active nucleus of TON 618 as a resolved system of clouds and rings. Instead, astronomers combine spectra, brightness, redshift, and physical models. The active nucleus is understood through consistency among these measurements. The measured luminosity requires a powerful energy source. The broad spectral features require fast gas. The overall behavior fits the model of a supermassive black hole surrounded by accreting material. Observations indicate this picture strongly, while the exact arrangement of every cloud and flow remains uncertain. The active galactic nucleus is therefore the central furnace of the quasar system. It is smaller than the host galaxy but brighter than the stars around it. It is driven by gravity but seen through radiation. It gathers gas inward, heats it, ionizes it, and sends part of its energy back outward. Within this compact region, the outer galaxy's material becomes the light by which the hidden black hole is known. The inward path has reached the active center, where the mystery of TON 618 begins to take its most concentrated visible form. Outside the deepest central region, but within the active nucleus, matter begins to organize into an accretion flow. Accretion is the process by which gas moves inward under gravity and gradually joins a central object or central system. Around a black hole, this movement is not a straight fall. Gas carries angular momentum, so it tends to circle the center. Instead of dropping directly inward, it spreads into a rotating flow, often described as an accretion disk when the material becomes flattened by rotation. At the outer edge of this flow, the gas is still far from the event horizon compared with the scale of the black hole itself, yet it is already under the command of the central mass. The material may arrive from the galactic core in uneven streams, clouds, or disturbed flows. Once it reaches the active region, collisions and pressure help it settle into a more organized rotation. This outer accretion zone is a transition region, where broad galactic gas becomes part of a compact engine. The disk is not a solid plate. It is a moving body of gas and plasma. Plasma is gas so hot or energized that many atoms lose electrons, leaving charged particles. These charged particles respond to magnetic fields, and magnetic fields help shape the motion of the disk. The gas orbits the center because gravity pulls inward while its sideways motion keeps it from falling directly. The balance is never perfectly calm. Friction, turbulence, and magnetic stresses shift energy and angular momentum through the material. For gas to move inward, it must lose some of its angular momentum, In an ordinary orbit, matter can keep circling for a very long time. In an accretion disk, internal stresses move angular momentum outward. Some gas gives up enough rotational support to drift closer to the center, while other gas carries extra angular momentum outward. This slow exchange allows the disk to feed the black hole over time. Without such a process, the gas would remain in orbit and the quasar would not shine with the same power. The outer accretion flow is cooler than the inner regions, though it is still energetic compared with ordinary interstellar gas. Cooler does not mean cold in a familiar sense. It means that the radiation produced there tends to emerge at longer wavelengths than the radiation from material deeper in. Depending on the temperature and density, parts of the outer disk may contribute visible light, ultraviolet light, or infrared emission after nearby dust absorbs and re-emits energy. The total light from the quasar is built from these layers of temperature and motion. The disk around an ultramassive black hole has a scale that differs from disks around smaller black holes. A black hole with tens of billions of solar masses has a much larger gravitational radius than a black hole with only millions of solar masses. The gravitational radius is a length scale set by the black hole's mass. Because TON 618 is inferred to contain an ultramassive black hole, the regions producing certain kinds of light may be physically larger than comparable regions around smaller active black holes. Yet the same basic physics applies, with gas orbiting, heating, and slowly drifting inward. The outer accretion flow may not be perfectly smooth. It can contain clumps, spiral patterns, waves, and unstable patches. Gravity from the central mass dominates, but the disk's own density, magnetic fields, and incoming material can create structure. Some regions may become denser and brighter, others may thin out. The disk may also be tilted or warped if incoming gas arrives from different directions over time. In a distant quasar, these details cannot be mapped directly, but they are part of the physical models used to understand variability and spectral shape. Radiation from inner regions shines outward onto the outer disk. This illumination can heat the disk surface and change the light it emits. Some of the observed optical brightness in quasars may come from disk material that is warmed by radiation from closer to the center. This means the outer accretion flow is not only heated by its own internal motion, it also responds to energy produced deeper inside the active nucleus. The surface layers absorb, scatter, and re-emit light, adding complexity to the spectrum. Above and below the disk, gas may rise in a thicker atmosphere. The disk is flattened by rotation, but it is not infinitely thin. Pressure gives it height, and radiation can lift material from its surface. Magnetic fields may help launch winds from the outer and middle disk. These winds carry gas away from the accretion flow and can shape absorption features in the spectrum. The presence of winds shows that the disk is not only a feeding structure, it is also a source of outflow, returning some material to the surrounding nucleus. The outer accretion flow must also connect with dusty material farther away. Dust cannot survive too close to the central radiation, but beyond a certain distance it can exist in clouds or a thicker surrounding structure. The boundary where dust begins to survive depends on luminosity. In a quasar as bright as TON 618, this dust survival distance may be large. The outer disk and dusty region together help shape how radiation escapes from the nucleus and how it is seen from far away. In this region, the brightness remains a sign of gravitational energy being converted into radiation. The gas releases energy because it moves through a deep gravitational field and because internal stresses turn organized motion into heat. The process is efficient, but not simple. Some energy becomes light, some remains in the motion of gas, some may help drive winds, some may be carried inward. The observed quasar luminosity is the outward expression of this hidden exchange. The outer accretion flow is therefore a broad rotating approach to the black hole. It is no longer the host galaxy, and it is not yet the innermost disk. It is the region where supplied gas becomes part of the central machine. Its matter circles, heats, shifts angular momentum, and begins the gradual inward drift that powers the visible quasar. In TON 618, this flow must operate on a scale and at an energy level consistent with one of the most massive black holes known. The details remain unresolved, but the essential picture is steady rotating gas enters the central environment and begins to turn gravity into light. Deeper within the accretion structure, the gas enters the hot inner disk, where conditions become more extreme and motion becomes faster. This region lies closer to the black hole, though still outside the event horizon. The inward path now approaches a domain where gravity is stronger, temperatures are higher, and radiation is more intense. The disk here remains a rotating flow, but its properties differ from the outer regions because of the increased energy released as matter moves closer to the center. As gas spirals inward, it loses gravitational energy. This energy does not vanish. It is converted into heat through friction, turbulence, and magnetic interactions within the disk. In the inner regions, this heating becomes very strong. The gas reaches temperatures high enough to emit large amounts of ultraviolet radiation, and in some cases even higher energy light. The brightness of the quasar depends heavily on this inner zone, where the most energetic part of the emission is produced. The speed of the orbiting gas increases as distance to the center decreases. This follows from the balance between gravity and motion. Closer to the black hole, a stronger inward pull requires faster motion to maintain orbit. The gas in the inner disk therefore moves at a significant fraction of the speed of light. These high speeds are not directly observed as moving objects across the sky. Instead, they are inferred from the broadening of spectral lines and from models that match the observed energy distribution. The disk is not only hot and fast, it is also dense enough to radiate efficiently. In some models, the disk behaves like a surface that emits thermal radiation, meaning radiation related to its temperature. Each region of the disk emits light characteristic of its local temperature, with inner regions producing higher energy light and outer regions producing lower energy light. When combined, these layers create a continuous spectrum that spans multiple wavelengths. For a quasar as luminous as TON 618, this combined emission becomes one of the dominant sources of its observed brightness. Magnetic fields play a significant role in this region. They arise from the motion of charged particles in the plasma and can become tangled and stretched by the rotation of the disk. These fields help transfer angular momentum outward, allowing gas to continue drifting inward. They may also contribute to heating by converting magnetic energy into thermal energy through processes such as reconnection, where field lines break and reconnect in new configurations. This adds to the already intense energy environment of the inner disk. Radiation pressure becomes more important in this zone. As the disk emits large amounts of light, that light can push on the gas. The balance between inward gravity and outward radiation pressure helps determine the structure of the disk. In a very luminous system, radiation pressure can puff up parts of the disk or contribute to the launch of winds. The exact structure depends on the rate at which matter is accreted and the mass of the black hole. For TON 618, the extreme luminosity suggests that radiation pressure is a significant factor in shaping the inner flow. The inner disk may not be perfectly flat. In some conditions, it can become thicker, especially when radiation pressure is strong. This thickness changes how light escapes and how different regions of the disk interact with each other. The geometry may influence the observed spectrum and the direction of outflows. However, the precise shape of the disk in TON 618 cannot be directly imaged. It is inferred from theoretical models that match observed brightness and spectral features. The motion of gas in this region is not entirely orderly. Turbulence is present, meaning irregular and chaotic motion on many scales. Turbulence helps mix material and spread energy through the disk. It also contributes to the transport of angular momentum. Without turbulence or similar processes, the disk would not be able to sustain the inward drift of matter needed to power the quasar. The presence of turbulence is supported by both theory and observations of variability in active galactic nuclei. Above the disk, a region of very hot, diffuse gas may exist, often referred to as a corona. This corona is not the same as a stellar atmosphere, but it shares the idea of a hot, extended region above a denser surface. In this environment, high-energy photons can be produced through interactions between electrons and lower-energy light. These interactions can scatter photons to higher energies, contributing to the X-ray emission observed in many quasars. While detailed properties of the corona in TON 618 are uncertain, similar mechanisms are expected to operate. The inner disk also reflects part of the radiation it receives from even closer to the black hole. Some light emitted inward or downward can strike the disk and be reprocessed, adding features to the observed spectrum. These reflections can carry information about the speed and gravitational environment of the emitting region. In nearer systems, such features help probe the effects of strong gravity. For a distant object like TON 618, such details are harder to extract. But the same physical processes are believed to be present. Time variations in the inner disk can occur as conditions change. If the rate of incoming gas varies, the temperature and brightness of different regions can shift. Magnetic activity may also cause fluctuations. These changes can alter the emitted light over time. Observations of quasars show variability across many timescales, supporting the idea that the inner disk is a dynamic environment rather than a steady structure. In this inner accretion zone, the conversion of gravitational energy into radiation reaches a peak. The gas is hot, fast, and dense enough to produce the powerful emission that defines the quasar. The disk extends inward toward the last stable orbits around the black hole, where gravity becomes even more extreme. The inward path is now close to the region where space and time are strongly curved, and where the boundary of no return lies just beyond. The hot inner disk is therefore a central stage in the visible story of TON 618. It is not the black hole itself, but it is the closest region from which light can escape. Its conditions reveal the scale of the central mass and the efficiency of the accretion process. As matter continues its inward spiral, the environment grows more extreme, guiding the exploration toward the regions where motion, gravity, and light approach their limits. Near the bright inner regions of the quasar, the gas does not only shine as a smooth flow of light, it also produces broad emission lines, measured features in the spectrum that reveal motion, energy, and composition. An emission line appears when atoms or ions release light at particular wavelengths. In a calm gas cloud, such a line may be narrow. In the active nucleus of TON 618, many lines are broad because the gas producing them is moving at very high speeds around the central mass. This broadline region is not a sharply visible ring or shell in direct images. It is inferred from the spectrum, where light from fast gas is spread across a wide range of wavelengths. Some gas moves toward the observer, shifting its light slightly toward shorter wavelengths. Some moves away, shifting its light toward longer wavelengths. Many clouds or streams move in different directions at once, and their combined emission creates a widened spectral feature. The width of the line becomes a measure of speed. The gas in this region lies outside the event horizon and outside the deepest invisible boundary, but it is close enough to feel strong gravity from the central black hole. Its motion is mainly controlled by that gravity. The faster the gas moves, the stronger the central pull must be, provided the gas is bound to the system. This relationship allows astronomers to estimate the black hole's mass. The method is indirect, but it is grounded in the same principle used to measure mass from orbital motion in many astronomical systems. For TON 618, broad emission lines are central to the mass estimate. The quasar's spectrum includes strong features from ionized gas, and the widths of these features indicate very rapid motion. Combined with the luminosity of the quasar, these measurements suggest an extraordinarily massive black hole. The method depends on understanding the size of the broadline region, which is related to the brightness of the active nucleus. More luminous quasars tend to have broader line regions located farther from the center, because intense radiation can ionize gas over larger distances. The broadline region is made of gas that is dense enough to emit strongly, but not so dense that all radiation is trapped. It is illuminated by the hot inner disk and nearby high-energy regions. When energetic photons strike the gas, atoms lose electrons and become ions. As electrons return or shift between energy states, the gas emits light at specific wavelengths. Different elements and ionization states produce different lines. Hydrogen, carbon, magnesium, and other elements can all leave signatures, depending on the temperature and radiation field. The clouds or flows in the broadline region may not be arranged in a simple sphere. They may form a flattened distribution related to the disk, a thickened cloud layer, or a mixture of inflowing and outflowing gas. The exact geometry remains uncertain, especially for a distant quasar like TON 618. However, the broad lines show that a large amount of gas is moving under the influence of the central gravity. The lines carry information from a region that cannot be resolved by ordinary imaging. One important assumption in mass estimates is that the gas motion is mainly gravitational. If radiation pressure, winds, or other forces strongly affect the line-emitting gas, the interpretation becomes more complex. In luminous quasars, radiation pressure can be significant. It may push on gas and change its motion, especially for material with strong absorption. Astronomers account for these uncertainties through calibration against other active galaxies and through comparison among different emission lines. Observations indicate that TON 618 remains an extreme ultramassive candidate, though any single numerical mass estimate carries uncertainty. The broadline region also responds to changes in the central light. When the brightness of the inner disk changes, the surrounding gas can brighten or dim after a delay. This delay occurs because light needs time to travel from the central source to the gas. In nearer active galaxies, measuring such delays allows a method called reverberation mapping. Reverberation mapping uses the echo of changing light to estimate the size of the broadline region. For very distant and luminous quasars, direct reverberation measurements are more difficult, so size is often estimated from established relationships between luminosity and broadline radius. The spectrum of TON 618 is therefore a layered record. The smooth continuum shows the energy of the accretion flow. The broad lines show fast gas close to the central mass. Narrower lines and absorption features show other gas at larger distances or along the path to Earth. In this section of the inward journey, the broad lines are the main guide because they belong to the region where the black hole's gravity becomes measurable through motion. Line width is not the only important property. The strength of a line shows how much emitting gas is present and how strongly it is illuminated. The shape of a line may hint at whether gas is rotating, flowing inward, or being driven outward. A symmetric broad line may suggest a range of balanced motions, while an asymmetric line can suggest additional structure or directional flow. For TON 618, the great distance and high luminosity make detailed interpretation challenging, but the broad features remain clear evidence of extreme central motion. The broad-line gas must survive in a narrow range of conditions. Too far from the centre, it would move more slowly and produce narrower features. Too close, the radiation may over-ionize it, stripping electrons so completely that certain lines become weak. The observed broad lines therefore arise from a region where density, radiation, and distance create the right conditions for strong emission. This balance marks a physical layer around the black hole, neither cold and distant nor swallowed and dark. The measurement of mass from these lines gives TON 618 its place among the most extreme known black hole systems. The inferred mass is often described in the range of tens of billions of solar masses. A solar mass is the mass of the Sun. Such a mass places the central object far above the black holes found in most galaxies, including the one at the centre of the Milky Way. The estimate is not a direct weighing, but a calculation from light, motion, and distance. Using the broadline region as the moving tracer, the broad emission lines therefore form a bridge between visible radiation and hidden gravity. They do not show the black hole's surface, because no such surface is visible. They do not show the interior, because no light returns from within the boundary. They show gas still outside, moving fast enough to reveal the depth of the gravitational field. In TON 618, these lines become one of the most important scientific clues, turning a distant point of light into evidence for an ultramassive black hole. From the measured light and motion around TON 618, the inward exploration reaches the question of mass and scale. The central black hole is inferred to belong to the ultramassive class, with estimates commonly placed in the range of tens of billions of solar masses. A solar mass is the mass of the Sun, used as a standard measure for stars, galaxies, and black holes. In this context, the number is not a count of stars gathered into one visible body. It is a measure of gravity concentrated inside a region from which no light can return. The mass estimate for TON 618 is extraordinary, because it exceeds the central black holes found in most known galaxies. The black hole at the centre of the Milky Way has a mass of about 4 million solar masses. Many large galaxies contain black holes with millions or billions of solar masses. TON 618 is placed far beyond these familiar examples. Its inferred mass reaches a scale where the word supermassive no longer feels sufficient in ordinary usage. So the term ultramassive is often used for black holes above about 10 billion solar masses. This mass is not measured by placing the black hole on any physical scale. It is calculated through the behavior of surrounding matter and light. The broad emission lines show gas moving rapidly in the central region. The luminosity helps estimate how far that gas lies from the black hole. When speed and distance are combined through gravity, they give a mass. The method is powerful, but it carries uncertainty because the true geometry of the gas is not fully known. Observations indicate an extreme mass, while the exact value depends on the calibration and assumptions used. A black hole's mass determines the size of its event horizon. For a non-rotating black hole, the radius of that boundary increases directly with mass. A black hole twice as massive has an event horizon twice as large. If the black hole in TON 618 has a mass of tens of billions of solar masses, Its event horizon would be enormous by human standards and large even by the standards of galactic nuclei. Its diameter would span a distance comparable to many times the scale of the solar system. This size does not mean the black hole is a solid sphere. The event horizon is not a surface made of material. It is a boundary in space and time. Outside it, light can still escape if directed properly. Inside it, all paths lead inward. The mass gives the boundary its scale. But the black hole itself is defined by gravity rather than by a visible edge. In distant observations, the horizon of TON 618 cannot be directly imaged. Its size is understood through theory applied to the inferred mass. The density implied by such a black hole can seem surprising. If the mass is spread conceptually inside the event horizon volume, the average density decreases as black hole mass increases. A very massive black hole can have a low average density by this simple calculation, even though the gravity at its boundary is extreme. This does not describe matter arranged in an ordinary way inside the black hole. It is only a way of comparing mass with the volume enclosed by the event horizon. The true interior remains beyond direct observation. The scale of TON 618 also affects the environment around it. A larger black hole has a larger gravitational radius, and the disk regions measured in units of that radius correspond to large physical distances. Gas orbiting close to such a black hole may move at relativistic speeds, meaning speeds where effects described by relativity become important. Yet because the central mass is so large, some orbital timescales can be long compared with those around smaller black holes. The system can be physically huge while still behaving as a compact source at cosmic distance. The luminosity of the quasar is tied to this mass through the balance between gravity and radiation. A more massive black hole can sustain a brighter accretion flow before radiation pressure strongly opposes infalling gas. TON 618 shines with extreme power, consistent with the central object of enormous mass. If a much smaller black hole produced the same luminosity, the outward pressure of radiation would be more difficult to reconcile with steady accretion. The large mass therefore helps explain the observed brightness. The growth required to reach such a scale is one of the important mysteries. A black hole begins from some earlier seed, which may form from the collapse of a massive star, the direct collapse of a gas cloud, or another early pathway. It then grows by accreting gas and by merging with other black holes, to reach tens of billions of solar masses by the time represented in TON 618's light. Growth must be efficient over long periods. Observations of quasars in the early universe show that massive black holes can grow quickly, but the precise routes remain an active area of study. Mass also shapes the black hole's relationship with the host galaxy. In nearby galaxies, central black holes tend to show broad correlations with the mass and motion of the surrounding stellar bulge. These relationships suggest linked growth between galaxies and their central black holes. TON 618 tests the high end of these patterns. Its inferred mass is so large that it raises questions about how the host galaxy supplies enough material and how feedback from the quasar affects further growth. Observations indicate the system is extreme, while its exact place within galaxy scaling relations remains uncertain. The word largest can have more than one meaning in this subject. It may refer to the greatest mass, the widest event horizon, or the most luminous active system. TON 618 is often described among the largest known black holes because of its inferred mass. Scientific caution is important, because black hole masses in distant quasars are uncertain, and new discoveries can change rankings. Within current understanding, TON 618 remains one of the strongest examples of an ultramassive black hole candidate, with a mass estimate that places it near the top of known systems. Its scale is therefore both numerical and conceptual. It is measured through solar masses, through the radius implied by general relativity, through the brightness of accreting gas, and through the speeds shown in the spectrum. Each measure points to the same conclusion: the hidden central object is not merely large, but exceptional. The mass cannot be seen directly, yet it organizes the surrounding light. It gives the quasar the gravitational depth needed to shine with such intensity. It turns TON 618 from a distant point in the sky into one of the most extreme known markers of black hole growth. Moving inward from the question of mass and scale, the exploration reaches the region defined by the event horizon. The event horizon is the boundary around a black hole beyond which light cannot escape. It is not a material wall, and it does not glow by itself. It is a limit created by the shape of space and time around a concentrated mass. For the ultramassive black hole inferred in TON 618, this boundary would be vast, set by a mass measured in tens of billions of solar masses. The event horizon is understood through general relativity, the theory in which gravity is not treated as a force pulling across empty space in the ordinary sense, but as the curvature of space and time near a black hole. This curvature becomes so strong that all future paths inside the horizon lead inward. A beam of light inside the boundary cannot travel outward to distant space, not because the light becomes weak, but because outward paths no longer lead outside. The horizon marks where escape ceases to be possible. For a black hole that is not rotating, the event horizon has a simple theoretical radius that grows directly with mass. Real black holes are expected to rotate, because they form from rotating matter and gain more spin through accretion and mergers. Rotation changes the detailed structure around the horizon, creating a more complex space-time geometry. The exact spin of the black hole in TON 618 is not known. Observations of distant quasars do not yet provide a clear direct measurement of this property, so the horizon's exact shape remains described by models rather than by direct evidence. The boundary itself cannot be seen. What may be seen, in nearer black holes, is a shadow-like region caused by light bending around the black hole and by the absence of light from inside the horizon. A black hole shadow is not the event horizon itself. It is an apparent dark area against surrounding glowing material, enlarged and shaped by gravity, for TON 618. Direct imaging of such a shadow is not possible with present instruments, because the object is too distant and appears too small in angular size, despite its enormous physical scale. If such a shadow could be resolved, it would appear as a dark central region surrounded by distorted light from nearby gas. The light would not travel in straight lines near the black hole. Gravity would bend it, allowing some photons to loop around before escaping. The observed shape would depend on the black hole's mass, spin, orientation, and the structure of the emitting gas. In TON 618, these details remain beyond direct sight, so the event horizon is known through the mass estimate and the physics of black holes rather than by an image. Near the horizon, the speed needed to escape approaches the speed of light. Outside the horizon, a particle or photon can still escape if it has the right path and enough outward direction. At the horizon, even light cannot move outward to freedom. This does not mean that an observer falling through would necessarily notice a solid crossing at that instant, especially for a very large black hole. The boundary is local in a subtle way, defined by the global structure of path through space and time. Its importance becomes clear only by considering where signals can eventually go. For an ultramassive black hole, the tidal forces at the horizon can be weaker than those around a smaller black hole. Tidal force is the difference in gravity between two parts of an object. Around a small black hole, this difference can be severe near the horizon. Around a much larger black hole, the horizon lies farther from the central concentration in terms of ordinary distance, so the difference across a small object at the boundary can be less extreme. This does not make the black hole gentle. It means that size changes how gravity is experienced at the horizon. The event horizon also sets a limit on information carried by light. Material outside the horizon can shine, scatter, and send signals outward. Material crossing the horizon can no longer send signals to the outside universe. This creates the observational darkness at the center of the black hole. Astronomers can study the gas before it crosses, the radiation produced by the accretion flow, and the gravitational effects on nearby matter. They cannot receive light from within the boundary. Around the horizon lies the photon region, where gravity can bend light onto highly curved paths. In the simplest non-rotating case, there is a special distance where photons can orbit in unstable paths. These orbits are not safe tracks where light remains forever in ordinary conditions. Small disturbances send photons inward or outward. Around rotating black holes, the photon paths become more complex. This region helps shape the shadow seen in direct images of closer black holes. For TON 618, it remains part of the theoretical structure associated with the inferred mass. The horizon is also connected to the last stable orbits for matter. Gas in the accretion disk can orbit stably down to a certain inner region. Depending on the black hole's spin and the direction of the orbit, inside that region, matter plunges inward more directly. The exact location of this transition affects how much energy the disk can release before material disappears beyond the horizon. A rapidly spinning black hole can allow stable orbits closer to the boundary in some directions, increasing accretion efficiency. For TON 618, the spin and inner disk details remain uncertain. The immense mass of the black hole means that the horizon's physical diameter would be enormous, but from Earth it is still far too small to resolve. Distance compresses even vast structures into tiny apparent angles. This difference between physical size and apparent size is central to the challenge of studying distant quasars. The black hole may be larger than the scale of planetary orbits, yet its boundary is hidden within a point of light at cosmological distance. The horizon is therefore present in the physics, but absent from direct view. The event horizon is the first true dark threshold in the inward path. Outside it, matter can reveal itself through light and motion. At it, the possibility of return ends. The black hole's mass shapes the surrounding disk, broadline gas, and quasar luminosity. But the horizon defines the black hole in the strictest sense. It is the boundary that separates the observable environment from the region that cannot communicate outward. In TON 618, this boundary is not seen, touched, or resolved. It is inferred with confidence from the same gravitational theory that explains black holes across the universe, and from the extraordinary mass required by the quasar's light. Just outside and near the boundary of TON 618's central black hole, gravity becomes the main subject. The region is not defined by matter alone, because matter may be sparse, falling, heated, or already gone beyond return. It is defined by the curvature of space and time around an enormous mass. In general relativity, space and time are not a fixed background. They form a connected structure that can bend, stretch, and shape the motion of everything within it. Near an ultramassive black hole, this structure becomes deeply curved. The curvature is strongest in the direction inward. Any object that moves close to the black hole follows a path shaped by that curvature. A planet around a star follows a curved orbit because gravity changes its motion. Near a black hole, the effect becomes far more extreme. Paths that would be nearly straight in empty space become sharply bent. Light, which has no rest mass, is still guided by the curvature of space and time. This is why a black hole can bend light around itself, and why the region near the horizon is visually distorted in theoretical models. Time also behaves differently near the boundary. To a distant observer, clocks closer to the black hole appear to run more slowly. This effect is called gravitational time dilation. It occurs because time passes at different rates in different gravitational conditions. Near the event horizon, the difference becomes very large. A signal sent from just outside the horizon would lose energy as it climbs away, and its wavelength would stretch. The light would become dimmer and redder to distant observers. This does not mean time stops locally for matter near the horizon. It means that time is measured differently depending on where the observer is located. For a black hole as massive as the one inferred in TON 618, the scale of curved space is immense. The same relativistic rule apply as they do near smaller black holes, but the distances involved are much larger. A region measured in gravitational radii may correspond to many billions of kilometers. Gas moving near the boundary can take long periods to complete orbits compared with gas near smaller black holes, even while moving at high fractions of the speed of light. The mass stretches the stage on which relativity acts. The strength of gravity near the boundary does not act like a simple downward pull on a surface. There is no surface underfoot, no solid edge, and no place where the black hole can be touched. Instead, the geometry of possible paths changes. Outside the event horizon, a path can still lead away. At the horizon and within it, all future directed paths lead inward. This is a statement about direction through space and time, not merely about speed. Even the fastest possible signal, light, cannot choose a route that escapes once inside. Tidal forces remain part of the region, though their character depends on mass. Tidal forces stretch objects along one direction and compress them along another because gravity differs across distance. Around a small black hole, these differences can become destructive well outside or near the horizon. Around an ultramassive black hole, the horizon is so large that the tidal difference across a small object at the boundary may be relatively mild. Farther inward, however, the differences increase. The calmness of the crossing, if described locally, does not remove the certainty of inward motion. The motion of matter near this region is shaped by the last stable orbits. Outside those orbits, gas can circle while gradually losing energy. Inside them, stable circular motion is no longer possible in the same way. Matter plunges inward, carrying whatever light it can still emit before crossing the horizon. The position of these orbits depends on the black hole's spin. Rotation can pull space and time around with it, an effect known as frame dragging. Frame dragging means that the rotating black hole twists nearby paths, influencing how matter and light move. The spin of TON 618's black hole is not known with certainty. If it spins rapidly, the inner structure of the accretion flow differs from that around a slowly spinning black hole. Matter orbiting in the same direction as the spin may approach closer before plunging inward, allowing more gravitational energy to become radiation. Matter orbiting against the spin behaves differently. These possibilities affect models of brightness and efficiency, but present observations do not fix the exact spin. The gravity near the boundary is therefore understood in general form, while some detailed features remain uncertain. Light near the black hole follows complicated paths. Some photons escape to distant space, some fall into the horizon, some curve strongly, passing around the black hole before moving outward. This bending means that an observer could receive light from parts of the disk that would otherwise be hidden behind the black hole. The image would be warped, with arcs and rings created by gravity. For TON 618, such features cannot be resolved, but the same physical rules govern the unseen region around its boundary. Energy also changes as matter moves through this gravitational field. Gas falling inward releases energy before it crosses the horizon. The efficiency of this release depends partly on how close stable orbits reach. A non-rotating black hole allows less energy extraction from the disk than a rapidly rotating one in favourable conditions. This is one reason spin matters in active galactic nuclei. The quasar's brightness comes from matter outside the boundary, and the curved space near the boundary helps determine how much of that matter's energy becomes escaping radiation. The region near the boundary is also where ordinary intuition becomes least reliable. Distance, time, and motion remain measurable, but their relationships differ from everyday experience. A clock, a beam of light, and a falling particle all follow rules that are consistent and precise, yet unfamiliar. The black hole does not pull light back like a material trap. It shapes the future paths available to light. It does not have a hard surface that matter strikes. It has a boundary beyond which the outside universe can no longer receive information. In TON 618, the gravity near the boundary is hidden behind distance, glare, and the limits of resolution. Yet the theory describing it is not invented for this object alone. It is the same framework tested by the motion of stars near the Milky Way's central black hole, by gravitational waves from black hole mergers, and by horizon-scale images of nearer black holes. These observations support the general picture, though they do not reveal the specific details of TON 618's horizon region. The inward exploration therefore rests in a zone where the visible signs grow faint and the geometry becomes central. Matter may still glow outside the boundary, and light may still escape from some paths, but the defining feature is curved space and time. The enormous mass of TON 618's black hole gives this curvature a vast scale. Its gravity organizes motion, slows distant measures of time, bends light, and sets the direction of all paths near the threshold. The region is not silent because nothing happens there. It is silent because its deepest rules are carried outward only by the last light that escapes. At the inward edge of what can be inferred from light and motion, the question of formation becomes quiet and difficult. The black hole in TON 618 is not only massive in the present observation of its ancient light, it is massive at a time when the universe is still younger than it is now. This creates a central problem for astrophysics. A black hole can grow by consuming gas and by merging with other black holes. But growth takes time, and the available time in the early universe is limited. The existence of an ultramassive black hole therefore requires a history that is efficient, sustained, or built from unusually large beginnings. The simplest path begins with a stellar remnant. When a very massive star exhausts the fuel in its core, gravity can overcome internal pressure and the core can collapse. In some cases, the result is a black hole with a mass of several solar masses or more. Such a black hole can grow if gas falls into it. It can also merge with other black holes. This pathway is known to occur in the universe, and gravitational wave detections show that black holes do merge. Yet a small seed formed from a star must grow by many orders of magnitude to reach tens of billions of solar masses. That kind of growth is possible only under demanding conditions. Another possible pathway begins with a larger seed. In some early environments, a massive gas cloud may collapse more directly, avoiding ordinary star formation and producing a much heavier black hole seed. This is called direct collapse. A larger starting mass reduces the amount of later growth required. Direct collapse is supported by theoretical models, but direct observational proof remains limited. It remains uncertain how often such seeds form, and whether they are common enough to explain the most massive black holes seen at early cosmic times. A third contribution may come from repeated mergers. Galaxies grow by merging, and their central black holes may eventually sink toward the center of the combined system, and merge as well. Over long periods, this can build larger black holes. In dense early environments, where massive galaxies assemble rapidly, mergers may be frequent. However, mergers alone may not be enough unless they occur together with strong gas accretion. After two galaxies merge, gas can be disturbed and driven inward, feeding the central black hole and increasing the brightness of the quasar. Gas accretion is the main luminous growth channel. When gas falls toward the black hole, it forms a disk, heats, and radiates. The same process that makes TON 618 visible also increases the black hole's mass. The rate of growth depends on how much gas is available and how efficiently radiation pushes back against further infall. If the quasar shines near the Eddington limit, the black hole can grow rapidly, but still not instantly. Sustained feeding over long intervals is needed, interruptions. Feedback and lack of fuel can slow the process. The Eddington limit marks a balance between inward gravity and outward radiation pressure under idealized conditions. If radiation becomes too strong, it can push gas away and limit accretion. In real systems, the situation can be more complex. Gas may arrive unevenly, flow through dense streams, or be partly shielded from radiation. Some models allow short phases of growth above the standard Eddington rate. Such phases could help build very massive black holes more quickly. Observations indicate that rapid early growth occurs in some quasars. While the duration and frequency of these faster phases remain uncertain, the host galaxy must supply the material. A black hole cannot grow in isolation. It needs gas delivered from larger scales into the central region. This requires a chain of processes that begins in the galaxy and its surroundings. Gas must enter the galaxy, cool, lose angular momentum, and move toward the center. Stellar bars, galaxy interactions, turbulence, and mergers can all help. Each step is imperfect. Some gas forms stars, some is heated, some is expelled by winds. Only a fraction reaches the inner accretion flow. For TON 618, the final mass implies that this chain has been highly effective at some stage of its history. Feedback complicates the story. As the black hole grows and shines, it releases energy into the surrounding gas. This energy can push material away, heat it, or prevent it from cooling. Feedback may slow further growth by reducing the supply of fuel. At the same time, feedback is a natural result of the accretion that builds the black hole. The system therefore contains a tension. The black hole needs gas to grow, but its own luminosity can disturb the gas reservoir. The enormous mass of TON 618 suggests that growth has continued despite this self-limiting effect, at least during important phases. The timing of this growth is also important, because TON 618 is observed through light from the past. Its black hole has already reached an extreme mass by the epoch represented in that light. The history leading to that state must occur earlier still. This pushes the starting point back toward the first generations of galaxies, and perhaps toward the first massive black hole seeds. The early universe contains dense regions where matter collapses quickly, and such regions may provide favorable conditions for rapid black hole formation. Yet the exact path from early seed to ultramassive quasar remains unresolved. The mystery is not created by a lack of physical laws. The laws of gravity, radiation, gas motion, and stellar evolution provide several possible routes. The uncertainty lies in the sequence, efficiency, and environment. It is not known whether the black hole in TON 618 begins as a stellar remnant that grows with exceptional speed, as a massive direct collapse seed, as a product of repeated mergers, or as a combination of these pathways. Observations indicate the final mass and active state. They do not preserve a complete record of every earlier stage. The word mystery, therefore, has a careful meaning. It does not mean that the object is beyond science. It means that current evidence does not yet identify one unique formation history. Models can reproduce parts of the growth, and observations of other distant quasars provide comparisons. New surveys continue to find massive black holes at early times, adding pressure on theories to explain how such objects grow so quickly. TON 618 remains one of the most extreme examples in this wider question. In this region of the inward path, the focus rests not on a visible layer, but on a history compressed into the present mass. The central black hole carries the result of earlier collapse, feeding, merging, and feedback. Its formation is written indirectly in the scale of its gravity and the brilliance of its quasar phase. Observations indicate that an ultramassive black hole exists at the heart of TON 618. It remains uncertain which early route gives rise to such a mass, and how long each phase of growth lasts. The mystery is quiet, measured, and unfinished, held within the enormous weight of the central object. Beyond the event horizon of TON 618's central black hole lies the region that cannot be observed from outside. No light, particle, or signal from within this boundary returns to distant space. The inward exploration reaches a limit not because instruments are weak alone, but because the structure of space and time prevents information from crossing outward once it has passed inside. This region is therefore not dark in the ordinary sense of being unlit. It is dark because it is closed to observation. The interior of a black hole is described by general relativity, but it is not directly tested by sight. The theory predicts that once matter crosses the event horizon, all future paths lead inward. The direction inward becomes as unavoidable as the passage of time outside the black hole. A falling object does not choose a path back toward the wider universe, because such a path no longer exists within the geometry. This statement applies to light as well as matter. The boundary has already removed the possibility of return. For an ultramassive black hole, the crossing of the horizon could be locally uneventful for a small falling object, because tidal forces at the boundary may be relatively mild compared with those near smaller black holes. Yet this does not make the interior accessible or safe. The important change is causal. Causality describes which events can influence other events. Inside the horizon, events can influence deeper interior regions, but not the outside universe. The silence of the interior is therefore a silence of communication. The path inward continues toward conditions that are not fully understood. In the simplest solutions of general relativity, matter and curvature move toward a singularity, a place where density and curvature become infinite in the mathematics. A singularity is not treated as an ordinary physical object. It is a sign that the theory has reached a limit. Most physicists expect that a deeper theory, involving quantum gravity, is needed to describe the true conditions at such scales. Quantum gravity is the still incomplete effort to unite gravity with the rules that govern very small particles. For TON 618, the interior cannot be distinguished by direct measurement from the interiors of other black holes, except through the external properties of mass and possible spin. Black holes in general relativity are described from outside by a small set of properties: mass, rotation, and electric charge. Astrophysical black holes are expected to have little net electric charge, because surrounding plasma tends to neutralize it. Mass is strongly inferred for TON 618, while spin remains uncertain. These outside properties shape the horizon and the space around it, but they do not open a view into the interior. If the black hole rotates, the mathematical interior becomes more complex than that of a non-rotating black hole. Rotation changes the structure of horizons and the predicted paths inside. However, these interior predictions depend on idealized solutions and may be altered by realistic matter, radiation, and quantum effects. Observations from outside cannot confirm the detailed inner structure. Scientific caution is therefore necessary. The exterior evidence supports the presence of a black hole, but the interior remains beyond empirical reach. The mystery of the interior is different from the mystery of formation. Formation concerns past events that may leave indirect traces in the surrounding galaxy. Gas and mass. The interior concerns a region from which no trace can emerge after crossing the horizon. Matter falling in may increase the black hole's mass, spin, or other external properties, but its detailed internal state cannot be read by distant observers. The black hole accepts energy and momentum, while concealing the fine structure of what enters. This concealment gives rise to the information problem. In quantum physics, information about the state of a system is not expected to disappear completely. In classical black hole physics, material crossing the horizon seems to become inaccessible, while black holes can slowly lose energy through Hawking radiation, a theoretical process in which quantum effects allow black holes to emit radiation over immense timescales. For a black hole as massive as TON 618's, this process would be extraordinarily weak and slow, far beyond any practical observation. The information problem remains a major theoretical question, not a measured feature of this specific quasar. The interior also changes the meaning of size. Outside, the event horizon gives a measurable scale related to mass. Inside, ordinary spatial intuition no longer applies in the same way. The geometry does not describe a room or cavern hidden behind a surface. It describes a region where paths through space and time are directed inward. The black hole is not hollow in the familiar sense, and it does not contain visible landscapes. Such images belong to imagination rather than observation. The scientific description remains geometric, quiet, and limited. The matter that once shines in the accretion disk loses its visible identity after crossing the horizon. Before crossing, it may emit radiation, shape magnetic fields, and join the luminous flow that makes the quasar visible. After crossing, it becomes part of the black hole's total mass and motion as measured from outside. The detailed atoms, ions, and fields no longer send messages outward. The bright quasar and the silent interior are therefore connected by a boundary that separates observation from absence. In the case of TON 618, the contrast is especially strong. The system is known because it is among the most luminous quasar sources, yet the object at its center is defined by a region that emits nothing outward from within. The greatest brightness surrounds the deepest darkness. This is not a contradiction. It is the nature of accreting black holes. Light comes from material before it disappears. Darkness belongs to the boundary and what lies beyond it. The inward path ends here because science itself draws a line between what is inferred and what is seen. The black hole's mass can be estimated. Its horizon size can be calculated from that mass. Its surrounding gas can be studied through spectra and brightness. Its formation can be modelled with uncertainty. Its interior cannot be observed. The most accurate description is therefore restrained. Observations indicate an ultra-massive black hole at the center of TON 618. General relativity describes an event horizon and an interior beyond return. It remains uncertain how the deepest interior should be described when quantum effects become essential. The final region is not a place of detail, but a limit of knowledge. It holds no visible surface, no returning light, and no direct signal. Around it, gas shines with enough power to cross the universe. At its boundary, escape ends. Within it, the known paths lead inward, beyond observation. The largest black hole candidate becomes, at its center, not an image of size, but a quiet absence surrounded by evidence. Its mystery remains steady, carried not by speculation, but by the silence that begins where light can no longer leave. The distant light of TON 618 rests as a quiet record from an earlier universe. Around it, space expands, gas drifts, dust absorbs and releases warmth, and gravity gathers matter into forms that can shine across immense distances. The quasar remains visible because material outside the black hole still gives up energy before crossing the boundary of no return. Its scale is measured through motion, brightness, and the careful reading of spectra. The black hole itself does not offer a surface or a direct image. It is known by the way surrounding gas moves, by the power of the central glow, and by the size implied through general relativity. Observations place it among the most massive black holes known, while the exact value and growth history remain uncertain. The path inward ends at a limit. Outside the horizon, light carries evidence, gas circles, heats, and radiates. Clouds glow in selected wavelengths. Dust softens and reshapes the energy. Stars of the host galaxy hold the wider setting. Inside the horizon, no signal returns. The central darkness is not empty in a simple sense, and it is not visible in any ordinary way. It is a region where known paths lead inward, and where deeper physics remains unfinished. TON 618 therefore remains both measured and mysterious. Its surrounding light belongs to science, observation, and careful inference. Its interior belongs to the edge of present understanding. The largest black hole candidate is not only an object of size, but a reminder that the universe holds places where brightness and silence meet. Around the darkness, matter shines. Beyond the boundary, the record stops. The remaining image is calm, distant, and still, held in ancient light crossing the deep universe.